All right. So now we will. You already know the CUDA programming model, right? So you are familiar with the API for CUDA programming, and now we're going to introduce some more detail about the GPU architecture from the hardware aspect. So you can see that how the CUDA API abstract the hardware architecture. And we do need to know the detail of those hardware architecture because that's tightly coupled to the optimization technique. So that's why it is quite challenged to optimize the code on GPU because you have to really familiar with the hardware architecture to do that, and they are tightly coupled. And unfortunately, no, or maybe fortunately, GPU is keep changing rapidly. So the architecture are keep changing. So it can provide more powerful features and much higher computing power, right? So as a result, the architecture change, you have to keep learning it, and so you can. That's how you can get even better performance. Okay. All right, but of course, here we will only talk about the very basic thing. So those things, of course, will definitely stands for all the GPU, and not just the NVIDIA GPU. Usually for the other no, all other brands of GPU as well, because most of them are quite similar. Okay, right. So we will talk about the architecture from the execution point of view and the memory point of view, because that's all we care, right? When we do the computation. Okay? So we start with the execution. That's from the threats point of view. Okay. So I think you should already familiar with, right, the concept or the view from the CUDA API. So you have a thread, you have thread block, and you have a grid, which is a kernel, right? And each of them maps to some hardware objects, right, or entity, right? The thread maps to the core, a single core. And we say it's a scalar processor because it's actually a core of a SIMD processor. Okay, and the thread block will map to the string processor. And as we mentioned, even a string processor contains multiple SIMD processor. Okay, and finally, is the grid. Grid means a GPU device because a single kernel can only run on a single GPU. There's no way to run, at least for now, there's no way to run a single core kernel across multiple devices. Okay? But of course, as we mentioned, a single GPU can run multiple kernels concurrently through multiple processes or through multiple GPU stream. Okay? Okay, so I think this is what you should have already know, right? So for the stream processor, because it has a on-chip memory, the per block share memory, that's why the variable stored on the share memory can be accessible by all the threads of a thread group, right? And and of course, because each stream processor have many cores, so a stream processor can execute multiple thread blocks at the same time, as long as the stream processor has sufficient available cores. Okay, and however, the thread blocks, right, because they could be scheduled to different stream processor, and they will be run on those stream processor independently. So there's no order, right, of execution between those thread block. And unfortunately, there's also no any synchronization API supported from CUDA because we want the stream processor to execute their workload independently, so we can have a more scalable hardware architecture. In the next lecture, we will introduce the kernel decomposition technique, which is a technique we use to create a barrier across thread blocks. Okay. All right, and so we know the thread, we know the thread block, we know the grid, and what's new here is WAP. Okay, so what is a WAP? WAP is a unit of a 30, is a group of 32 threads within a thread block. And a WAP is actually corresponding to the SIMD processor we mentioned. Okay, and as you can see here, most of the GPU has a SIMD processor with 32 core. That's why the size of a WAP is also 32 threads, because each thread needs a single core, right? All right, so so you can imagine for the threads within the WAP, they can be executed in parallel physically, because a SIMD processor, you have to all the threads, right? All the threads need to execute exactly the same instruction at the same time. So that's why they can be executed in parallel physically. Okay. On the other hand, for the threads that is within the thread block, but on different WAP, then they are only run in parallel logically. That means we think they are run in parallel, but actually it not be, right? That's why we introduced the thread synchronous API, right, in the kernel code that try to synchronize the thread within the thread block. So even for the thread within the thread block, we need to synchronize them because they are not executed in parallel physically. Okay, if they are assigned to different WAP. Okay, and this 32, right? This 32 threads, they are actually decided according to their thread index. So according to the thread index, you can know exactly whether those threads are within the WAP or on a different WAP. Okay. For example, thread 0 to thread 31 will be scheduled in the first WAP. Okay, and so on and so forth. So the thread index is really important because it even indicate how those threads will be executed on the hardware. And you need to know that because right, the synchronization behavior will be dependent on it. Okay, and also later on in the next lecture we talk about some memory optimization, and all those optimization could only be applied within the WAP, right? Between WAP, because they may not even run in parallel, so you cannot do any optimization between them because they are not supposed to be run in a synchronous way. Okay, so only the threads that runs in parallel physically, we can control the memory access and try to merge their I/O or try to make their parallel I/O more efficient. Okay, all right. And so you can see from the hardware aspect, okay, we mentioned just composed of multiple SIMD processor. So you can see just as example, right? If you check it from the GPU spec, you can find out some of the information like saying the maximum number of active blocks per string processor is 8. Okay, so that's the indication that this string processor only has 8 SIMD processor in it. That's why he can only run the active blocks. Oh, so sorry, it should be this one, right? Active WAPs is 48. So that means this string processor only has 48 SIMD processor. Okay, and those WAPs comes from the blocks, right? The thread blocks. And so if you want to run the blocks on a string processor, you also need to reserve the register for those all the threads within that thread block. So That's why there's also an upper limit for the number of active blocks per stream processor. Okay, because you may only have limited number of registers on those stream processor. Okay, so you can see here you can only run 8 thread blocks on a stream processor. Okay, how many WAPs from each blocks doesn't really matter. So all those limits, so you have all those hardware limits, constraints for your execution, and they may not need to be no need to be have any corresponding relationship. There are just some limitation has to be opposed on different level. So you have to meet all of them. If you violate one of them, then you will have trouble to run your code. So basically, you have to make sure throughout your execution, you fit all those constraints. Okay. All right. So you can see, for example, the maximum because of those two constraints. So you can see that the maximum number of active threads per SM should be the two numbers multiplied together. But that doesn't mean you can always reach that number, right? It all depends on, for example, maybe your blocks, one of the blocks, has a fewer number of WAPs, then you are still bounded by this A active blocks constraint. Okay. So anyway, you have all those hardware numbers to figure out whether you can really fully utilize your cores or not. Okay. And remember, all those numbers are from the hardware aspect. So we said nothing about whether those blocks coming from a single kernel or multiple kernels, right? That's another level of consideration when you utilize your GPU. Okay, so you may just run one kernel on the GPU or multiple. No matter how many of them running on the GPU, still for each SM you can only run 8 active blocks on it and 48 active WAPs on single SM. Okay. All right. So as as what I mentioned before, right? You will find that the number of active WAP or the number of active threads actually are more than the number of physical core, because if you multiply together, right, you will find out that the number of threads that can be scheduled on a SM is more than the actual GPU core on the SM. And the reason is because we have memory store problem, right? So the GPU will try to context switch between those WAP when there's a memory store happen on the WAP. Okay, so this is a view of a single. You can imagine it as a view for a single CD processor. So it can execute 32 threads at a time from some WAP, right? And as long as there's a single thread from that WAP try to access memory, then you will face a memory store problem. So in order to make sure the GPU core does not idle during the memory store, the GPU threads will do a context switch to another WAP, right? And a WAP that is ready to run, without waiting for memory access. So we can keep switching between those WAP to utilize our computing power. And for the stream processor or for the SIMD processor, it doesn't care, the WAPs are from which thread blocks or from which kernels. They all break down to the WAP. Okay, and you can just schedule any WAPs from any thread blocks from any kernel that is available to run right now. Okay, so that's why he can keep switching between them to hide the memory access time. Okay. All right. So let's finish this before we have we finish this lecture. So because as we can see, for a WAP is executed by a single CD processor. So all the threads need to execute exactly the same instructions. So you have a branch. If you have a branch in your CUDA code, and unfortunately it forced the thread within the WAP to execute different instructions, then what happened is the CD processor will execute the instruction, both instruction in your branch, okay, and then select the one that's depending on your branch results, okay. So you actually execute the code twice, not just once, on each of those threads, okay. So that's why we call the WAP diversion problem. Okay? So how to solve it is, we can try to branch at the WAP level. This one of the optimization technique. Sometimes you will see those weird code that try to rewrite it based on the WAP size, mostly because of this reason, because all the optimization will only be applied at the per WAP level. So that's why you need to know the behavior of those threads within the WAP individually, because if they are in different WAP, then you don't need to worry about how they get executed or their memory pattern. All you need to care about is the behavior of the threads within the same WAP. Okay. All right. Yeah. So we have other examples. So sometimes it's very hard to avoid the WAP divergence, like the case here. If every thread try to execute different code, then you will run into this issue and your performance will degrade significantly. So that's why for GPU, usually we still follow the single program, multiple data programming model to make sure all the threads execute the same instructions. Okay. All right. So so we'll leave the rest of the content for our next lecture. Okay.